should make a start. Evening, everyone. Thank you for joining us this evening for another interesting talk. This evening, we've got Dr. Lucy Kay from COVI, who's going to be talking about the core surprise, what's inside a plate boundary fault in Scotland. I'm sure most of us will enjoy this one. I'm definitely sure I will. So over to you, Lucy.
Okay, thank you. So hi everybody. So I'm currently an engineer and geologist for COVI, but today I'm going to talk to you about my PhD research that I completed at the University of Strathclyde over the past few years. So the title of tonight's talk is Core Surprise, What's Inside a Plate Boundary Fault in Scotland. So just this research, for those who are interested, is published in the Journal of the Geological Society and as a feature article in the Geoscientist magazine last year, and also just at the beginning of this year as a published article in the Earth and Planetary Science Letters. So major earthquakes can occur on any large fault, but 90% of earthquakes are associated with plate boundary faults. Therefore, understanding the internal structure, for example, the fault core composition, fault core thickness, and the geometry of the fault is crucial, because the structure and properties of faults control how and where earthquakes rupture, nucleate, and propagate, which in turn limits the size of the earthquake or the amount of radiated seismic energy and consequently surface damage. So for example, the 1999 magnitude 7.7 earthquake along the Cholungpo plate boundary fault in Taiwan saw significant variations in slip and ground motion at different locations along the fault, which is shown in these images here. And as you can see, there's different fault motions therefore resulted in different casualties, different damage. And this ranged from burst dams to collapsed buildings and even fallen temples. So the southern end of the plate boundary fault had small displacement and minimal damage. And subsequent field investigation of this fault related the changes to variation in the fault structure. For example, the width of the clay at the different parts of the fault and the geometry and what rocks were on either side of the fault. Therefore, understanding the internal structure of plate boundary faults is crucial. So just to give you a little bit of background and information on faults for those who have never worked on them. So faults are not just a line on a map as they're normally shown, they're actually a zone of variably deformed fault rock. A fault zone is typically split into a 3-component model. So you've got the host rock, which is the rock on either side of the fault core, which is in the middle, and it accommodates most of the fault slip and the maximum displacement, and then the bounding fracture-dominated damage zone. So the fault core can range from a few centimetres up to tens of metres wide and contains deformed fault rocks such as clay-rich gouge, breccia or cataclasites, which are just different names for various types of fault rock. And the damage zone which bounds this fault core comprises of fractured host rocks, smaller faults, veins, and folding at all scales. But the key distinction is the damage zone doesn't have any shear. It's all accommodated in the core. So despite the fact that I said that 90% of global seismicity occurs on plate boundary faults, our knowledge of their internal structure is lacking, as the opportunities to directly study them are few. This is because field studies are biased towards features that can be exposed and are visible at a scale that humans can realistically observe and measure. So obviously this biases studies towards small faults, as you can see it all. So for example, as shown in this bottom image, the graph, this shows data from multiple fault studies, and it shows that faults typically get wider on average with increasing displacement. So this trend, this displacement thickness trends, represents a growth trend where low displacement faults represent a stage of early growth and are narrow, but as they get longer over time, they become more complex and the fault core therefore gets wider. However, the vast majority of faults in that dataset, pretty much all of them, are from intraplate faults. So these are the faults that are within the interior of tectonic plates and not at the boundaries. So plate boundary faults with large displacements have largely been excluded from this dataset. But recently, there have been several drilling projects that have been undertaken at active plate boundary faults to explore how the internal structure of these fault zones influence slip behaviour. And scientific findings for each of the projects, no matter what plate boundary it is, highlights the presence and importance of these clay-rich fault rocks, which is gouge, through influencing how the fault behaves and its earthquakes. So for example, this slide shows the San Andreas borehole that, well, it was the San Andreas Fault Observatory at depth borehole that drilled through the San Andreas Fault, and drilling revealed that the internal structure of the San Andreas Fault consists of wall rock of contrast in lithology. So on one side you've got quartzo-feldspathic wall rocks, and on the other side you've got serpentinitic wall rocks. And then in the middle you've got this gouge with clasts. But such projects are expensive. So the bill for the San Andreas Fault alone, this project alone, was $25 million. And they're also limited in what they can tell us, because it's one borehole, so effectively they just sample us, basically limited 1D transect a fault across the fault, which limits the ability to therefore capture the variability. So what I'm talking about tonight, what about the internal structure of an ancient plate boundary fault in Scotland that's relatively well exposed, unlike the San Andreas? So this is the picture of the Highland boundary fault in northeast Scotland, and it's an important fault that's been studied in UK geology for many years, but nobody has actually looked at the internal structure of it. So comparable to the San Andreas fault, you've got these wall rocks of different lithologies on either side. So you've got the quartzo-feldspathic wall rocks, which belong to the Dalradian supergroup, which underlies most of the Scottish Highlands. And then on the south side, you fault, like the San Andreas, you have these serpentinite that come from oceanic crust. So like I say, but unlike the San Andreas fault, the Highland boundary fault is relatively well exposed, but nobody has looked at its internal structure. So we went to the beach with permission from the Scottish Natural Heritage to dig it up. And this just shows I was digging the beach. So just to give a bit of context for those that are not familiar with the Highland boundary fault, it's a mature crustal fault with a very long and complex history. So it extends for over 240 kilometres from the northeast of Scotland in Stonehaven, which is just south of Aberdeen, trends southwest through Loch Lomond, and then across the Isle of Bute and into the Isle of Arran, with possible extensions into Ireland. So as I've mentioned, it separates the distinct terrains. So you've got on the north this Grampian, which is the Dalradian metamorphic sedimentary rocks, and on the south you've got Midland Valley rocks of different ages. So if you're ever driving up north on the A9 and you go from low-lying rocks, low-lying flatland in the Midland Valley, and you then come into the hilly terrain, you know you've crossed the Highland boundary fault as it separates these distinct terrains. So this picture here just shows the fault running through the middle of the bay at Stonehaven, and this image on the right shows the Highland boundary fault if you're standing at the top of Conic Hill on Loch Lomond, and you can see it, it's marked by these lines of islands running through the middle of the loch. Excuse me, just So unlike drilling projects along the San Andreas, the Highland Boundary Fault exposures at Stonehaven, which is just south of Aberdeen, actually provide us with a rare opportunity to study the internal structure of a major plate boundary fault. So first of all, I remapped the exposure at Stonehaven and then did 6 across fault transects known as structural logs to capture the variability as shown in these black rectangles on the map, logs 1 to 6. So on this map on the north, in the grey, you've got the Dalradian, and then in the orange, purple and green, you've got the ophiolitic rocks. So the Highland Boundary Fault is thought to have been active during 2 events of the Caledonian orogeny in the early Ordovician. But like the San Andreas, it has grown and evolved through time. Early fault motion during the Grampian orogeny was believed to be reverse, and then it was reactivated into sinistral strike slip during the Acadian orogeny. But the magnitude of strike slip displacement is debated. And like other terrain bounding crustal scales Caledonian faults in Scotland, such as the Great Glen Fault, it wouldn't be surprising if the Highland Boundary Fault accommodated minor motion at younger ages due to the North Sea extension or North Atlantic opening. So yeah, just to reiterate, in the north we've got the Dalradian, south you've got the Highland Boundary Fault, and in the middle there's this fault core. This just shows a different image of the fault looking southwest across the bay, but you can clearly see it running across the bay here. And after digging and exposing the fault at these several different localities, it revealed a remarkable sequence of fault rocks. So at all localities, it consists of a single fault core bound by these damaged zones of distinct terrains. And this log on the right just shows the sequence of fault rocks. So in the south, you've got the Highland border ophiolite, which is subdivided into 3 different units. In the middle, you've got the fault core, which in places has 4 different units. And then on the north, you've got the Dalradian, which again can be subdivided into different units. So just starting from the bottom of the log in this purple unit in the Highland border ophiolite, I'll just go through each unit and just give you a little bit more detail about what was observed. So starting with the Highland border ophiolite. The first unit is a carbonated serpentinite, shown in this picture, and it's comprised of a chaotic network of cross-cutting calcite veins, and it's cut by localized subhorizontal fractures that display an alteration halo, as you can see in the zoomed in images. And the fractures have an anastomose and conjugate geometry, with the alteration halo about 3 centimeters either side of the fracture. So moving up towards the main slip plane, second unit in your ophiolite, you get this what's called an Ophecarbonate. It's basically just a dolomitized serpentinite unit. This unit formed from the alternation of a serpentinite, like was the previous unit, via a carbonate or CO2 rich fluid. So in this unit, you see veins that are about 2 to 10 centimeters thick, and they're filled with multi-phase carbonate. So in the middle, you've got this very fine-grained dolomite, and then you've got this calcitic lining on either side, and the veins are generally aligned parallel to the Highland Boundary Fault. This slide just shows a section, a thin section of these multi-phase veins, and you can see that the calcite, which lines the vein walls, displays a dogtooth epitactyl texture, which is indicative of crack seal growth and extensional opening mode fractures. So it tells us a bit about how the fault moved. So I'm not going to go into any of the detail explaining where the data behind the stereo nets, but basically it's all from our field data on these veins that we saw in this unit. And basically the data shows that these veins provide evidence of early dextral reverse motion on the Highland boundary fault. That's the main thing you really need to take from those slides. Actually, there's two phases of early dextral reverse motion that this the ophiolite units show us. So in order to constrain the isotopic composition and the fluid sources from which this carbonate in the ophiolite units formed, we carried out delta 13C and delta 18O isotopes, and the results showed us that the first unit, the carbonated serpentinite, which is shown as these purple dots, is typical of a magmatic signature, and the Ophecarbonate, which was the unit with the veins, is typical of a marine signature. And your alteration halos, which was the halo around the fractures, a mixture between the two. So your hypothesis is that these units of the ophiolite formed by hydrothermal alteration by seawater with addition of magmatic CO2. Could go into a lot more detail about this, but we'll leave it at that for now because it's just important to tell you this information for the story of how it evolved, which we'll go through at the end. Just skip that one there. So back, what's inside the fault core? So the fault core, as I said, consists of 4 distinct units that remain unmixed. So you've got this localized green gouge, which is just above the finger in this top left image. Then you've got a blue gouge of high plasticity, a red foliated chaotic breccia with clear structural fabrics, and a red Cracobrachium with large elongated lenses of the wall rock. And surprisingly, they remain unmixed despite it being such a large offset fault. So I'm just going to go through and describe each of these fault core units individually. So the first one is this green gouge, which is a relatively thin zone, only about 30 centimeters thick. And it consists of about 50% clay, which is mixed clay, mixed illite smectite chlorite. And it was only observed at one locality, so it could either represent a zone of localized alteration, or it could have been once a lithology that extended all the way along the fault, but this is only what's left of it. This image just shows us some thin sections of this green gouge under the microscope, and my annotations of it. So the green gouge consists of very small rounded clasts embedded within this green-brown fine-grained clay matrix. I did some analysis of the thin sections from all the fault core units to try and compare them. So here I'm just presenting the average clast size, area, circularity, etc. But I'm not going to go into the numbers. All we need to remember is these clasts are very small and they're also circular. So moving slightly further away from the main slip plane of the Highland boundary fault, you come into this blue gouge, which is of high plasticity, and it's exactly like modelling clay. In fact, one member of our team even managed to model a fish in the field. It contains small clasts, and it's very impermeable, and again has a similar mineralogy to that green gouge, where it's nearly half of it's clay with the rest of it being quartz, and it's mixed chlorite, illite, smectite clay. These are the thin section and my annotation of the thin sections, and you can see that some of the clasts and matrix within this gouge have a preferred orientation. although the foliation can deflect and wrap around the small clasts. So for instance, in this sample on the left, the clasts and fabrics are aligned 15 degrees anti-clockwise to the Highland boundary fault in Rideau shear geometries. And on the image to the right, again, the fabric is aligned at high angles to the main slip plane of the Highland boundary fault in Rideau shear geometries. So this provides us evidence of past movements on the fault, and it's also clearly evidence that it's undergone shear in strike slip motion. As I've just said. So again, this slide shows us some of the thin section images from these samples under the microscope. And typically within the blue clay, the clasts are sub-rounded to rounded, spherical to elongate, and composed of not just a single mineral, they're aggregates of clasts. And in some instances in this bottom left image, it looks like a snowball where you've got clay wrapping around the clasts. But some clasts have rounded edges, as this one on the bottom left shows, whereas some have more tapered, elongate geometries, like the middle second one in on the top right, which shows that there's been a combination of shearing and chemical alteration. And some clasts have also display wings and display wings and strain shadows, which again is suggestive of this shearing. So again, I'm presenting the numbers from my analysis, but all we need to know or remember is that the clasts in this blue gouge, as you're moving further away from the main slip plane, are larger and less spherical than the green gouge. Surprisingly, there you found some ancient microfossils within this blue gouge unit, and these included bryozoans, which, talking to someone at the Natural History Museum, said that they belong to the order Fenestrata, which are now extinct. You've also got echinoid spines and brachiopods. Importantly, this just confirms that this is not just clay, you've modern day clay that you find on a beach. If you needed any more evidence that there was faulting related clays, this is it. They also have implications for the mechanics and the timing of the growth. It's surprising that they still survived, but unfortunately I wasn't really able to do any more work on these, so their presence remains somewhat a mystery. But as we're moving further away, you come into, from the blue gouge, you can then come into that red unit that was foliated and had the clear structural fabric. So this image here just shows the contact that was in the field between these two units. And again, the contact itself and all the alteration within the contact shows us evidence of shear. So this is this red foliated chaotic breccia, and it consists of subangular, circular to elongate clasts embedded in this dark brown to red matrix, and it's got red hematitic foliations which define the clear structural fabric, and the fabric itself, as shown in this rose diagram at the right, is aligned with the Highland boundary fault, but it can anastomose and wrap around these smaller clasts. So these are the thin sections from this unit. And again, you can see that they have a preferred alignment. So again, they're all aligned within Rideau shear geometries. The clasts themselves display an internal fabric and they're highly altered. However, actually in the clasts themselves don't display any evidence of the shear or the wings or anything like that from the blue gouge. So again, presenting the numbers here from my analysis, but all we need to remember is that these are they're becoming larger and more angular, less circular as we're moving away from the fault. So the last of this fault core units is this, what we call a red Cracobrachium. And this unit consists of large lenses of the Dalradian wall rock and up to 2.3 meters in length in places. And the long axis of these clasts are aligned parallel to the Highland boundary fault. So just coming back to what have been the main thing to remember, so those clasts were obviously very large. So as you're moving further away from your fault, your clasts are becoming larger and more angular. So in your green gouge, you had these very small circular clasts, slightly larger in the blue gouge, but more circular. Then they became a bit more angular, a bit larger, and then obviously you get the very large clasts in the red Cracobrachium. So it just gives us, the way that they are, gives you a bit of information about how the fault mechanics of how the fault moved. So it's suggested that these clasts are plucked off from the Dalradian wall rock and then just rolled and fractured and become smaller and smaller as they're incorporated into the fault zone. But one other thing to note from the fault core is the mineralogy of it. So XRD revealed that the mineralogy of the blue gouge and the green gouge, so it was illite, smectite and chlorite, and that's consistent with the Highland border ophiolite. So it's suggesting that these gouges are derived from the Highland border ophiolite units, whereas the mineralogy of the red clay was a bit different. There was no chlorite in this, and it was illite, smectite and kaolinite. So that has a similar mineralogy to the Dalradian wall rocks in the north. So it suggested that the red clay was derived from the Dalradian. So there's two different mechanisms going on within your forming your clays. Also, it has to be noted that each of these fault core units are not present at every locality along the fault. So going back to my message when I was talking about the San Andreas fault at the beginning, a borehole is a 1D transect across a fault. It can't capture the variability. So these are the structural logs that I did at the different locations along the Highland boundary fault. And every unit is internally variable and varies in thickness. So for instance, the green gouge is only observed at one locality, whereas as is the red Cracobrachium, they're only observed at two different localities. So like I said, each unit is internally variable and varies in thickness at different locations along the fault. So the total thickness of the fault core varies from about 3 meters in one place to about 10.7 meters in the other, which is quite a difference over a relatively short area or short distance. So in summary, I started off with the question, what's inside a plate boundary in Falkland, Scotland? So as I've just discussed, the answer is a quite structurally and lithologically variable fault core that ranges from about 3.7 to 10.7 meters wide and 4 distinct units that all vary in thickness. So the green and blue gouges are derived from this side of the fault from your ophiolite, whereas your breccias are derived from this north side of the fault from your Dalradian. But all the clasts within each fault core unit belong to the Dalradian. And like I say, they become smaller and more circular as you go towards the main fault plane. So the question remains as to why these Dalradian fault blocks are present in every unit, which implies a degree of mixing, but overall your units are not mixed. So this is my summary of the history of the Highland boundary fault, which as you can see, well, at just the Stonehaven section only, which as you can see is quite complex. So just briefly give a quick overview of what I think is happening. So the first stage is this alteration of your purple unit on the map, which was that carbonated serpentinite with the fractures and the alteration halos, chemically altering that to your Ophecarbonate, which was the origin unit with the carbonate veins. And as if you remember back to the stereo nets, those veins showed us evidence of reverse motion. So all that happened at an early stage during reverse faulting. There's some paleomagnetic studies which suggest that this CO2-rich fluid, which dolomitized the unit, occurred 260 million years ago. But the next stage of faulting must be all your formation of all these different units within the fault cores. So these, there's some small scale faults, redo shears in the Ophecarbonate, that offset the veins. Therefore, all these redo shears and strike slip motion must have happened after the reverse motion at some point in time. So first of all, you're starting to deform that Ophecarbonate unit with redo shears. Then you're starting to break down the Dalradian wall rock, and you're starting to form these clasts. You're going to start breaking down the Dalradian first because it's a weaker unit compared to the Ophecarbonate, which is now really strong. Like in the field, you couldn't even break it with a hammer, it's that strong. But after you then metamorphose your Dalradian, that will become harder than that. So then you'll start, oh sorry, I've missed the stage, as you're then incorporating all your clasts into the fault core and it becomes smaller. The next stage is once you metamorphose the Dalradian, you're going to start altering the other side of the fault, which is the ophiolite units. So then I'm suggesting you get this chemical processing of the Ophecarbonate, and you're forming your green and blue gouge. Whether the green gouge is localized, you don't know. But this is all happening by fluids coming in along these previously, along the redo shears, and you're gradually breaking down that rock and forming clay, and then into this blue gouge, which you've got all the evidence of the shears and the clasts that have been reworked into shear fabrics. And so I think they're distinct units, as there's been a difference in the way that the wall rocks have been processed through time. So you've got your red foliated breccias that were formed first from the Dalradian wall rocks, and you've got the plucking of the clasts. And then your blue gouge forms at some point after that, due to the alteration of the serpentinitic wall rocks along the shear fractures. So the mechanical properties of the fault have ultimately changed through time, which will have affected the fault's ability to host earthquakes. But there's one other question that arose, was, well, why does this matter, and how similar is the Highland boundary fault to other plate boundary faults? So if you can remember back to the very beginning when I gave an introduction of faults and I showed that graph, and that faults get wider, typically get wider with increasing displacement. And this increase in width occurs due to the way that the faults grow. But the vast majority of that data set was in intraplate faults, and plate boundary faults have largely been excluded. So in order to determine how similar the Highland boundary fault is to other plate boundary faults, I compiled all the data that I could from the literature on plate boundary faults from all the drilling studies, for example, in the San Andreas fault, the Alpine fault, the Taiwan Cholongpu plate boundary fault, and a few others, the Japan trends, for instance. And I unified a way in which they were defined. So for instance, I only took the studies that clearly defined the width and composition of the fault core as being distinct from the damage zone. So this shows my data for intraplate faults only, which again, similar to other studies and other that have compiled all these data, intraplate faults do typically get wider the more displacement and the larger they become. But based on this relationship, you would expect large displacement plate boundary faults with displacements greater than 10 kilometers to be follow this trend and be up here. However, they do not. So we found that plate boundary faults, fault core thickness is distinct from this trend, and that they're all anomalously narrow, and they don't show the same trend of increasing thickness with increasing displacement. Instead, they're all bound by a minimum and maximum value between 0.07 meters and 35 meters thick. And in order to test whether this was related to their structure, I then compiled schematic structural logs like I did for the Highland boundary fault. So these are my logs down here, which I just showed you. So compiled them for all the other faults that I could. And in places, the Highland boundary fault is similar to other plate boundary faults. For instance, it's comparable to the red foliated chaotic breccia, the Highland boundary fault, that unit with the clear structural fabrics, is comparable to what you see in the San Andreas fault, which is a highly sheared foliated clay that wraps around centimetre scale class of wall rocks. And like the Highland boundary fault, the San Andreas clays have been interpreted to form from the shear enhanced reactions between both wall rocks. But on comparison to all the available data from plate boundary faults, the fact that they all have narrow fault cores doesn't appear to be related to the host rock or the way the fault's moving, the fault type, whether it's a strike slip fault or whether it's a convergent plate boundary, or the number of fault core strands, the geometry of fault. These all vary, but the plate boundary faults still remain narrow. So we can only really say that the Highland boundary fault is comparable to other plate boundary faults in terms of fault core thickness. But this in itself actually has implications for how earthquakes behave. So just for the purpose of time, because we could be here a very long time if we go into all this detail, but basically I then compiled and compared the data between seismic moment, which is essentially a measure of earthquake magnitude, and the average displacement for plate boundary and intraplate faults. And the data shows that for a given value of average displacement, plate boundary earthquakes typically have a greater seismic moment and therefore hence a greater earthquake magnitude than intraplate faults. So during an earthquake, the total energy, which is shown in this equation at the bottom left, is partly consumed by the fault, by fracturing the fault, creating a slip surface, and partly consumed the energy is required for the slip to occur. So this is E, F, and Eg in the equation. You don't need to know what it means, but E, F, and Eg are basically the energy that is consumed by the fault in order for it to slip and create new surfaces for it to slip. Whereas ER is the energy that is radiated to the surface as seismic waves. Therefore, it is inferred that plate boundary faults, because you've got a greater seismic moment, you must have a higher radiated seismic energy to create more magnitude earthquakes. Therefore, plate boundary faults don't process intact rocks as much during seismic events as intraplate faults, so they're consuming less energy allowing more energy to be radiated for the surface. But in comparison, intraplate faults, they'll consume more energy, therefore less energy is available to be radiated to the surface, and then you get more, you get smaller magnitude earthquakes. So in intraplate faults, you've got complex geometries, you've got wider fault cores, so you're going to need to consume more energy, which therefore less energy reaches the surface. I know that's quite complex, but I can answer your questions at the end. So in summary, because plate boundary faults are narrow, because plate boundary faults, are narrow, because of this, for this reason, they do not consume as much energy as intraplate faults during earthquakes, allowing more to be radiated to the surface, creating higher magnitude earthquakes. So just to summarise, this lecture basically just gave you a very brief overview of the structure of the Highland boundary fault and its outcrop to microstructure scale, which makes a valuable contribution to the global dataset of plate boundary fault zones for which data is limited. And it also has similarities to other fault systems hosted in similar mineralogy, such as the San Andreas, and even sections of New Zealand's Alpine Fault. So the Highland boundary fault consists of these 4 structurally and mineralogically distinct fault cores, which all varies in thickness, and the units remain distinct due to differences in how the wall rocks have been processed through time. Your fault core thickness is comparable to other plate boundary faults. For example, all plate boundary faults have narrow fault cores, which has implications for earthquake energy and understanding how earthquakes behave between plate boundary and intraplate fault systems. So one significant implication of all this work is that plate boundary faults have evolved structural characteristics that allow them to efficiently dissipate seismic energy, and this helps explain why deformation is localized within them and has significance for the development and maintenance of the entire plate tectonic system. This is just a list of the references, including the reference to the published paper for this work. So thank you for listening. Are there questions?
Thank you, Lucy. That was very interesting. Do we have any questions for Lucy? Let's check the chart. You can also unmute if you like to ask questions, if you're not using the chat. Okay, we have one from Sheila. Sheila Peacock says, thank you, great talk. Have you any idea how deeply buried your section was when it was active?
Not for definite, no. However, it can't have been buried, for the clays to be formed, it can't have been buried that deeply. It must have been passively exhumed from a relatively shallow depth, a couple of kilometres. Otherwise, if it was any more than that, you wouldn't still have your clays preserved.
Okay. Got another one from Ben Bull. He's asked, do field relationships show any relative ages between the core units?
Only for, like I say, that for the blue, I didn't actually explain this very well, but in the image I showed you the contact between the the blue gouge and the red foliated chaotic breccia. I forgot to mention this in the talk. There was actually pockets of the red clay within the blue gouge. Therefore, the red clay has to have been older for it to be incorporated as lenses within the blue gouge. But it's only, like I say, I don't know exact dates or ages, but I am in the process of hopefully trying to date them, so we'll know for definite.
Thank you for that, Lucy. Any other questions for Lucy? Will you be going back to do any more work on your site, or any unanswered questions?
Probably the main thing for me is the date of it all, the date that the clays were formed. Talking to some people at the BGS, they see similarities in they see similar blue clay within other large faults in Scotland, strands off the Great Glen, which they've looked at and dated to be Carboniferous. So for me, probably it's just trying to pin down the ages, but I don't plan on going back to the site myself anytime soon. But you could look at other, like I say, that was only a small section along such a large fault, so you could look at other places if it was possible to dig it up.
And of comparisons.
Yeah.
Mike said, you might have missed it, but why might the fault zone thickness be relatively so variable over 0.5 kilometers?
It's how can I answer this? I don't actually know the main reason for it, but it's observed everywhere on all faults. So if you think back to the first slide on the Taiwan earthquake, in some places it's so many meters thick, in some places it's in the other. And then for my compilation of trying to see why all those structural logs, I couldn't see an obvious relationship. So I don't know why. I think it's a combination of just everything, to be honest. It's not just one thing that you can pinpoint down.
Yeah. It is an interesting one, though, in terms of variability. Yeah.
It might be to do with like what wall rocks are on either side of the fault, but in this case for the Highland boundary fault, that's the same in this one section. So I'm not sure.
We have Jeremy says, thank you for the nice presentations. Thank you. Any more questions? Okay. There aren't any more questions coming up. Okay. I guess you answered all the questions during your talk. I've got a couple of comments coming in. One from Peter saying, thank you, really interesting talk. It was quite interesting, and like I say, it's a subject that most of us are familiar with, especially from uni, and it's quite interesting to see someone give a talk on it. We hardly ever have applied geology talks like this, so it's quite good. Janice Nori says, an interesting talk, Lucy. Thanks. Did you compare your fault to any of the Great Glen fault exposures?
Not during my PhD, no. However, at Covey, we're working on a project at the Great Glen fault at the moment. So I'm planning to do some boreholes through there. So I will do in due course. But like, it wouldn't be surprising, like I say, people at the BGS have observed a similar blue clay off strands off the Great Glen Fault, so it wouldn't be surprising if you found this blue clay at other large faults in Scotland.
Mike Jones, he says, thank you. I was tweeting so many things from the talk that I thought I might have missed it. Yeah, he's enjoyed your talk as well. And that's on Twitter now at the moment as well, what we've been talking about. Are there any more questions, or we can wrap up? I think we can stop here. Oh, I've got another one from Naomi. She says, may I add my thanks. I visited the HBF as an undergraduate. It has been great to see an expert talk on it. Yeah. Thank you, Lucy.
I wouldn't call myself an expert, but
yeah, no, thank you very much for your talk, Lucy.
You're welcome.
Before we wrap up, just to remind you, we have our next talk next month. It's by Dr. Stefan Lautenschläger, and he's going to be talking about Jurassic brain teasers using modern technology to get inside the heads of dinosaurs and other fossils. Again, the talk will start at 7, so it'll be good to see you all again. Thank you for attending tonight. Hopefully you have a great evening. Thank you. Bye.
Thank you.
Okay. We've got a busy evening ahead.
Pardon?
We've got a busy evening ahead.
Just trying to get a toddler to bed.
Fine. It's going to be fun. Let me stop sharing.
Thanks for that anyway.
Thank you very much. The talk will be available on YouTube, and we'll get in touch once that's done, so you can have a look as well.
Okay. Thank you.
Thank you.
Bye.
Bye. Mm-hmm.